Morning, boys and girls. It is Thursday. It is May 14th. And today I'd like to quickly review the concept of convection because convection is actually occurring inside of our planet in two areas. The one area that I'm highlighting today, the upper mantle or the asthenosphere, will find that convection plays a very important role. So let's do a quick review of what the asthenosphere is. It is that portion of the mantle known as the upper mantle. It is a plastic or semi-solid rock. It's not liquid. I want you to understand that, but it's somewhere in between a true solid and a liquid. So we like to describe it as being plastic-like. If you recall, I described it as being almost the consistency of silly putty. And that's something good to keep in your mind's eye. And what's really important about the upper mantle is we believe that it is convecting or flowing, very similar to the motion in the lava lamp. Now, why does that occur? Well, let's go over the motion in the lava lamp. Okay, so we have a lava lamp. You guys took a look at my red lava lamp, and we see immediately, if we just make a quick observation, that we have globs of wax that rise from the bottom of the lava lamp and globs of wax that sink. And it's a continuous cycle of rising and then sinking, rising and sinking. So what's really happening in the lava lamp? Well, you know, boys and girls, it's heat driven. And most of you, when I asked you to respond to the bell ringer of how a lava lamp works, many of you actually said it has something to do with heat. And you're absolutely right. This has everything to do with a form of heat transfer, how heat moves. Heat moves on planet Earth and in planet Earth in just one way, from areas of warm to cold. This is a kind of heat transfer called convection. So what are the steps? There are four basic steps. So we have a light bulb in the bottom of the lava lamp. The light bulb actually transfers heat directly to the fluids in the lava lamp. It transfers those heats and is able to heat up those fluids in the lamp because the lamp sits right on top of the bulb. So that's called a form of heat transfer called conduction. If you're physically touching something, it conducts heat. We are not really going to focus on conduction here. We're focusing on the motion inside of the fluids, and that's a different kind of heat transfer. So why is it that the wax rises? Let's start with that. Well, the bottom of the lava lamp is hot because that's where the light bulb is. The fluid rises because heated molecules actually spread apart from each other and expand, much like if you could envision the molecules and you could see them. Look at this picture to the right of the slide. So we have molecules that actually spread away from each other, and that does something to the density of the substance. The density actually will go down or decrease. And when density decreases, the substance becomes less dense and floats to the surface. Remember, less dense objects float. So we have a heated fluid rising from the bottom of the lava lamp because it's hot and less dense. Now, as that fluid or globs of wax rises to the top of the lava lamp, it's naturally now going to cool off because it's not on top of the heat source anymore. So as the wax rises toward the top of the lava lamp, it begins to cool. Now, it cools, and at that point, the molecules do something different. Whereas when they were heated, they spread out. Cool molecules actually come together, and that's called condense. Very similar to if we were standing outside very cold and we didn't have our jackets on, we all might huddle close together to conserve our heat. Well, molecules come and huddle together when they're cool as well. When molecules do that and condense together, it actually affects the density of the fluid. The density now increases. So if you have an increase in density, that means more dense. the fluid now sinks to the bottom of the lava lamp. Now, gravity is always a force that acts upon everything on planet Earth. So the sinking motion also is happening because of the force of gravity. But I want you to remember, cold fluids sink, hot fluids rise. So we have this colder or cooler wax sinking because the density now increases. And this process continues just as long as that lava lamp is turned on and stays on. And that process is a form of heat transfer called convection. And convection, by definition, is the transfer of heat by the movement of a heated fluid. And fluids in science are either liquids or gases. And we're going to apply this to the upper mantle very soon. So I'm going to say fluids are liquids, gases, or semi-solids. Those things that can naturally flow because their molecules are not as densely packed together. So a quick review. We have the lava lamp working because of heat. Heat is transferred from the light bulb to the liquids inside of the lamp. The wax actually absorbs more heat and rises to the top because its molecules spread apart or expand from each other, and that causes the density of the wax to decrease. This is why we have the rising wax heading toward the top of the lava lamp. As the wax moves away from the heat source, it now begins to cool. So we clearly have a temperature difference from the bottom of the lamp to the top of the lamp. The bottom of the lamp is hotter, the top of the lamp is cooler. So that cooling wax starts to sink, and it does that because the molecules come closer together, and that affects the density. It makes the density increase. So we have more dense wax that sinks. And then we have the force of gravity that helps in the sinking motion of the convection current that is really taking place in the lava lamp. So we have convection, rising or heating, rising, cooling, sinking, heating, rising, cooling, sinking. Now, convection, as I said, is a transfer of heat from warm areas to cold areas by the motion of a fluid. A fluid could be a gas, so convection actually occurs in air. For example, warm air rises, cool air sinks. It occurs in liquids, much like a pot of soup. We looked at a pot of soup both in the gizmo and then in the short reading assignment that I had you do a couple of days ago. So we have convection occurring when we have warm water or warm soup rising and bubbling. It seems to bubble when you boil soup. Well, it's bubbling because it's rising from the bottom. It's so hot. And as that soup rises toward the surface of the pan, boys and girls, it does lose heat energy. So it loses thermal energy. It's slightly cooler than below at the bottom of the pan, so it begins to sink. So we have a heating, rising, cooling, sinking, nice little circular convection current here in the soup. Now, convection occurs now because of three different factors. The first important factor is temperatures differences within a fluid. You have a warmer area and a cooler area. You also, therefore, have density differences in a fluid because a warmer area is going to affect the density and make it less dense, the fluid. A cooler area is going to make the density increase or become more dense. And that has everything to do with the behavior of molecules. When you add heat to molecules, you have a lot of kinetic energy there. The molecules speed up and start moving all over the place like crazy, and they move away from each other. That affects the density of the fluid. It actually makes the density less dense. It decreases the density. Take heat away, the fluid cools. So now we have less energy, and so those molecules have less energy too. They slow down and they start to condense or come closer together. That causes the density to increase, and that makes the fluid start to sink. That sinking process is also affected by the force of gravity, because the force of gravity is always at play on planet Earth, helping to push everything down toward the center. So the three causes of convection would be temperature differences, density differences in the fluid, and the force of gravity. Please remember, when a fluid is heated, its density decreases or becomes less dense. When a fluid cools, its density increases or becomes more dense. Now, why are we learning about lava lamps and bubbling soup? Well, because those are really good analogies to what's going on inside of planet Earth's asthenosphere. Remember, the asthenosphere is that gooey kind of plastic-like semi-solid rock, similar to the consistency of silly putty. We have, scientists believe, convection currents occurring in that area in planet Earth. Now, in order for convection currents to occur, we need to have a heat source. So where's the heat coming from inside of our planet? Well, it's coming from the core, because that's the hottest section of planet Earth. And it's also coming from the mantle itself. Remember, the temperature of planet Earth, as we dig further into it from the surface, just increases. Very, very hot. The center of planet Earth, the core, is about as hot as the surface of the sun, about 10,000 degrees Fahrenheit. So it is hot. So we have heat from Earth's core and mantle causing convection currents to occur in this semi-solid asthenosphere. Now, these are very, very slow moving, because we're talking about rock here. We're not talking about liquid. We're talking about semi-solid rock moving ever so slowly. So very similar to the lava lamp in a boiling pot of soup, we have the hot, less dense columns of rock rising up into the asthenosphere. At the top of the asthenosphere, that hot material spreads outward horizontally and naturally begins to cool, because now I'm further away from the heat source, the deeper mantle and the core. It pushes the even cooler material further outward until that cooler material gets so cool that it starts to sink. Why does it start to sink? Because its density now increases. It becomes colder. The particles of molecules of rock start to condense, and we have an increase in density. So a sinking of that mantle material back toward the inner Earth. Again, as that occurs, it gets heated up again and just continues the cycle of heating, rising, cooling, sinking. In this case, it's heating, rising, cooling, sinking rock. So we have these nice convection cells, which is just that continuous cycle of heating, rising, cooling, sinking, occurring, we believe, all within the asthenosphere. Now, how do we know this, and how do we even come up with this? This is why we're learning about this, because we have to remember the asthenosphere is the upper mantle. It is convecting, we believe. Remember, on top of the asthenosphere sits Earth's lithosphere. We live on the lithosphere. We live on the continental crust of the lithosphere, the upper portion of the lithosphere, which is the crust. Remember, the lithosphere is the crust in the uppermost mantle. It's solid and it's rigid and it's cracked into huge pieces called tectonic plates. And that name tectonic comes from a Greek word called tecton, which means to build. Now, this is the current picture of, it's actually a pretty accurate picture of all of the cracks in Earth's outer shell or lithosphere. More on this coming up very soon on how we know exactly where the boundaries of these tectonic plates are. But we do know. Now, the lithosphere is rigid, boys and girls. So it's without motion on its own because it's solid rock. And now remember, underneath this rigid layer is motion. We have motion in the upper mantle. Now that's really important. We have a solid rigid layer sitting on top of a layer of moving rock. Now, how does that layer of moving rock, or how does convection in the asthenosphere affect the lithosphere sitting above it? Now you can take a quick look at this video that I have playing. I've taken out all of the audio on it. So we have a very hot center of the planet, the core. The core is radiating heat upward to the surface of planet Earth. We have this semi-solid asthenosphere that now starts to convect because of that heat transfer. We have this nice motion of convection currents in planet Earth. Those convection currents, boys and girls, actually do something to the lithosphere sitting on top of it. It actually moves the lithosphere. And I'm going to replay this video one more time so that you can see within the animation that convection in the asthenosphere causes those plates to move. Okay, so we have heat from the core radiating outward, causing convection in the asthenosphere. Sitting on top of the asthenosphere is the lithosphere. If you have motion underneath your feet, you're going to move. Well, we have motion in the asthenosphere, which causes the motion of the lithosphere. And boys and girls, those tectonic plates have been moving since the beginning of time for millions of years. Here is another view of the tectonic plate map. So here are all of the Earth's tectonic plates. And you'll notice when you look at this map, you'll see some little red arrows on it. The red arrows actually indicate how the plates move, and we're going to become really comfortable with this map and really understand just how to read it. This animation that I'm going to show you right now gives you a nice visual of convection in the asthenosphere, that up and down and all around motion, and these green tectonic plates sitting on top of the asthenosphere, which would be the lithospheric plates. All right, if convection is flowing and the lithosphere sits on top, well, it causes the lithosphere to move. And boys and girls, if you look really carefully, what happens? Those lithospheric plates actually sometimes come in contact with each other and build up the surface of the planet. And also, if you notice on this animation, convection currents actually look like they must also crack the lithosphere, and they do. So, big idea here. Convection occurs in Earth's asthenosphere. It does that because we have heat differences, temperature differences in the asthenosphere, hotter toward the bottom of the asthenosphere, cooler toward the top. Those heat differences cause density differences in the asthenosphere. Hotter areas are less dense and they rise, cooler areas are more dense and they sink. And we have this continuous cycle of heating, rising, and cooling, sinking rock in the asthenosphere. We have motion in the asthenosphere, and scientists infer that that motion in the asthenosphere is responsible for moving the tectonic plates of our planet all over our planet. Now we're going to learn everything about the theory of plate tectonics starting next week, and this was paramount to your understanding. It is not the last time you're going to see this. This is just a nice little preview.